Welcome to our first recorded Math 356 lecture. Okay, so let us begin where we left off in the synchronous lecture. Here we are. So let me pin myself. So let's get into things. However, let me first make some notes about this overall format. Okay, so while you watch these pre-recorded lectures, I want you to keep, I have a few notes for you, that might make this whole experience maybe a little bit better. There's some advantages to this format. Anyway, so here's what I suggest. So while you watch these videos, I think it would be best. Here's how it would be best for me personally to take advantage of these. Have laptop or whatever you watch this on a desk. Ideally, I know not everyone has a nice space like that, but to have a desk, ideally some scratch work, some scratch paper with pen or pencil, the book up as a PDF or as a physical thing open to the same section. So you can pause, take breaks, rewind, and absorb the material better, maybe make a note to yourself while you're doing these things. Okay, so this will be a little bit of a long video, so feel free to take breaks. You should probably every 20 minutes, half hour, 40 minutes, take a little break, stand up or walk around. And then there's some other things that we can take advantage of in this format. For instance, you can, something you cannot do in real life, even though you may want to, is you can increase the speed of the playback. There's a little button, the gear at the bottom right of the video where there is a setting for the playback speed, and you can increase it. Some people like that and go more quickly. Also, I'll have some timestamps in the description below the video, so you can jump around, maybe skip a working out an example that maybe you don't need to see worked out, or go to a particular section that you'd like to hear about. First of all, we're skipping section 2.3. We will probably not speak of it again. What we covered in the last class were this type of differential equation here called linear differential equation. They appear in this way where the x is only multiplied by a expression of t's. So remember to solve these equations, we have the following procedure, kind of a little trick, if you will. You calculate this auxiliary function that at first glance doesn't really have anything to do with anything, but it's e to the antiderivative of that a of t term. You calculate that, and then the trick is you realize that upon multiplying the equation, both sides of it, by u, the integrating factor, the left-hand side can be rewritten as the derivative of the product of the unknown function, in this case x, and u. From that point, solving the equation is a simple matter of, well, could be a hard matter, but it's you simply need to integrate both sides with respect to t, the variable, and then solve for the unknown function x of t. All right, so you have some exercise with that. We did some practice with that. Now let's move on to applying some of these tools. We have a little bit of a toolkit now. We know how to solve the linear equations and the separable ones. We can get into our first collection of physical problems, mixing problems. Okay, depending on what lecture you're in, I was able to read this statement or not. Here is the sort of problem that we'll be looking at in this section. Okay, so suppose you've got some tank of water here and you have some water flowing into it. it has some amount of, it contains 10 liters of water, say. You have some water flowing into it and some water flowing out of it. So in this situation here, the tank is 10 liters and water is flowing in with some salt concentration. So in this case, 2 grams of salt per liter is the concentration of salt in the water coming in. And the water coming in comes in at a rate of 4 liters per minute. Every minute, 4 liters comes in. So looking ahead, that's going to mean that 8 grams of salt comes in every minute. Okay, so water also flows out of the tank at the same rate, 4 liters per minute coming out of the tank, so that we keep a constant volume of 10 liters at the same time. All right, so let's say, so what is the question? The question is, suppose the tank starts with nothing in it. Now try to find a formula for the number of grams of salt in the tank at time t. How much salt is in the tank at any given time? That's not what I want to do. Okay, kind of a complicated thing. It's a little bit tantalizing because you think maybe you can just figure this out kind of algebraically with some elbow grease. But it turns out that freezing this problem as a differential equation is going to be quite elegant. All right, so let's try to approach the situation. So first we need to write down we have to identify something that we want to model with a differential equation, then write an equation for that function, and then solve it. And then reinterpret our solved differential equation in terms of what they're asking us to figure out. Okay, so first step, we should identify the relevant quantity that we want to write an equation for. So what we want to find out is number of grams in salt at time t. So let's give a name to that. So let's let x of t be the number of grams at t seconds after we start. Okay. Now, we want to find a differential equation that x satisfies. Well, let's make the following observation, not so mind-blowing, but x prime of t, that has the interpretation of the rate of change of the number of grams of salt in the tank. So there's 2 ways that the amount of salt in the tank changes. There's only 2 things happening to the tank. Some water comes in, some water goes out. So there's only 2 ways that it changes. The first will have a positive effect. The water coming in will increase the amount of salt. So let's write that down. So the rate of salt entering. And then there's a negative effect from the salt leaving the tank. That 4 liters per minute leaving the tank. So minus the rate at which salt leaves the tank. All right, so now let's try and figure out what each of these is. All right, well, we actually already mentioned what the first one is, the rate at which salt enters the tank. So it'll be, how much enters the tank? Well, it's 2 grams per liter times the rate at which the liquid comes in, which is 4 liters per minute. The units cancel and we are left with 8 grams per minute incoming. And then the rate at which salt goes out, well, that depends on how much salt is in the tank in the first place. So what is the concentration of salt in the tank at time t? This is where the differential equation way of thinking becomes relevant, because that depends on the function x itself. So the amount of salt in the tank will be, let's see, so it'll be the concentration. So that's x And so, so the concentration is X over 10. That's how many grams per liter there are in the tank at any given time. Remember, X depends on time. And then times, so to figure out actually the amount of salt leaving, you need to multiply the concentration by the rate at which the water leaves. So that's again 4 liters per minute. All right, so let's write down what we just found out. We just found a differential equation. X prime is equal to 8 minus X over, I guess, 2/5 X. Okay, or in other words, let's move the X to the other side. We get X prime plus 2/5 X is equal to 8. All right, that is a nice differential equation for the number of grams in the tank at any given time. Very good. Now, there's only one thing to do. We should solve this differential equation. This is going to be linear, so we're well equipped to deal with it. It's actually also separable, but let's think of it as linear, say. So, yeah, you could do either way. But let's note that, let's see, if we think of this as a linear differential equation, then the integrating factor is, well, just e to the antiderivative of 2/5 dt. So that's e to the 2/5 t. And so if we multiply the equation by e to the 2/5 t, then we'll realize the left-hand side becomes e to the 2/5 t times x prime, and the right-hand side is just the product of 8 and e to the 2/5 t. All right, and we go along and we solve this. We just integrate. So e to the 2/5 t times x is equal to antiderivative of this thing. It's not a big deal. Antiderivative will be 8 times 5/2 e to the 2/5 t plus c, or any number c. Or in other words, solving for x, remember, we want to know x, the number of grams of salt at time t. X itself is equal to, okay, now let's divide everything by e to the 2/5 t. We get, let's see, this is going to be, I guess, 4 times, that's 20, and then plus c divided by 2/5 e to the 2/5 t, so that's e to the minus 2/5 t, where c is any number. Okay, very good. However, this is a physical situation. There's an actual tank with water. There shouldn't be the ambiguity of the constant c. We should be able to figure out what c is. So, what's c? Well, there's one piece of information we haven't used yet. That's this part right here. The tank starts with no salt. So we haven't used that yet. Now's the time. So note from that, we can tell that at time 0, x takes the value of 0. At time 0, there's no salt in the tank. So x of 0 is 0. Now, in terms of the formula that we have, what does that mean? If I plug in 0 in for t, I just get 20 plus c, and I need that to be equal to 0. Because e to the 0 is 1. Or in other words, 20 is, or sorry, c is minus 20. So now we have our final answer. The number of grams of salt in the tank at time t is 20 minus 20 times e to the minus 2/5 t. If we wanted to, this isn't part of the problem, but if we wanted to do so anyways, what color do I want? We could do a little plot of this function, and it will behave in a way which is not so surprising. Whenever we do a new problem, you want to make sure that the answer makes some physical sense, because we already have some intuition about how tanks and salt work. So notice what happens with this function. Well, at time 0, it's equal to 0. And then over time, well, it'll limit. You can see if t goes to infinity, then e to the minus infinity, e to the minus t tends to 0. So this will limit to 20 as time goes to infinity. And in fact, the graph will look something like this. This is what x of t will roughly look like, which makes some sense. It will accumulate more and more salt. The amount of salt should not be unbounded. You don't imagine. Well, maybe you do, but it turns out that's not the case. That will over time tend to a specific number. Kind of the capacity for salt in this situation, some equilibrium value. Okay, very good. So this is our answer: grams at time t in minutes. Very good. So let's there will be a number of variations on this type of problem, but here's what I want you to be thinking of when you see a problem like this. So first of all, if you were just plopped into this situation with no guidance, it could be very confusing. And the thing to remember is the quantity to focus on, to write a differential equation for, so that you solve it and start to answer the question. The quantity to focus in on is the amount of stuff in the water. These are all of these problems are variations on particles of water, particles suspended in water, grams of salt or some pollutant in something else, what have you. But the thing to focus in is the absolute amount of stuff, not like as opposed to say the proportion of stuff. The thing to focus on is the amount of stuff in the water, number of grams of salt. That's what you want to write a differential equation for. To do so, you need to figure out what are the ways in which that quantity is changing. There's some salt coming in, maybe some salt going out. Read the problem to then try to express the difference of those two things. The rate of incoming stuff minus the rate of outgoing stuff. That will essentially be the differential equation, because x prime will be equal to that difference. And also, I don't know, sometimes word problems, they have some extraneous information. That's not going to be the case with these. I won't give you extra info. So in particular, that the fact that we started out with no salt in the tank is not going to be some extra information. You'll need to do it to use it to answer the question. Very good. Now these tank problems can get more complicated. Here's an example of one variation on the tank problem. Did I give myself some space? I didn't really. Okay. Well, let's take a look. So here is a souped up problem where we have two tanks. Let's label them number 1 and number 2. Where some water flows into tank 1, so it'll be tank number 1. Tank 1 then flows into a second tank, tank number 2, and this tank then flows, there's some water that flows out of that. All right, so here's what we know. Clean water flows into tank number 1 at a rate of 2 liters per minute. Clean water this time, as opposed to the salty water. What else do we know? Water flows from tank 1 into tank 2 at a rate of 2 liters per minute. And then water flows out of tank number 2 at a rate of 1 liter per minute. So we imagine tank number 1 is going to be at a constant volume, whereas tank number 2, its volume, the volume of liquid in there will be increasing over time. So, I mean, right off the bat, we can note actually that the volume of liquid in tank 2 at time t Okay, I mean, we read ahead a little bit and notice that tank number 2 starts empty. So it's not so hard to see that the volume of liquid in tank number 2, it'll just be, at time t, will be just t. Every minute that goes by, it'll accumulate 1 liter of liquid. Since it loses 1 every minute and it gains 2 every minute, so total it will gain 1. Okay. Now let's read through the rest of the problem. Okay, yeah, so tank 1 starts with 10 liters of water and 2 grams of salt in it, and tank number 2 starts empty. We want to know how much salt will be in tank number 2 after 30 minutes. So again, this is kind of a complicated situation because salt is flowing into the tank and clean water is running out of it, but the concentration of salt coming out of the first tank will change over time. So let's first give some names to things and try to make sense of the situation. So there's going to be 2 tanks we're interested in here, so we'll have to give names to 2 different functions. So let's see, let's call them x and y. X of t will be the number of grams of salt, I'll write that, in tank 1 at time t, and y of t will be number of grams of salt in tank 2 at time t. Okay, now let's write down a differential equation for each of these quantities. All right, so let's play the same game. We just need to make sure we're clear-headed about how much salt, the rate at which salt is incoming and outgoing for each of these tanks. So let's focus in on x first. Okay, what is the rate at which salt comes into tank 1? Well, it's going to be clean water, so no salt flows into it, so 0 for rate of incoming salt. Now, what about the rate of outgoing salt? Well, some salt leaves over time. It flows out at a rate of 2 liters per minute, and the amount will be the concentration of salt at that time in tank 1 times the rate at which it leaves. So now the concentration of salt at that time will be the number of grams of salt in the tank at that time, that's x, divided by the number of liters in that tank, which is 10. It starts out as 10 and it stays 10 because the amount of liquid coming in and going out cancel each other out. So divided by 10. So that's the concentration of, let me just maybe make a little note there just to be extra clear. This quantity here is the concentration of salt in tank 1. And then what do we need to multiply that by to get the amount that is leaving? But we need to multiply by that 2, the rate at which the water leaves. So 2 liters per minute. So in total, x prime itself is just equal to minus x over 5. Definitely separable and definitely not so hard to find a formula for it. Now, let's turn our, well, I mean, we'll do that in a second, but let's turn our attention to y. Y is a little bit more complicated. So let's think, how does tank number 2 behave? Well, we have some water coming in. What is the concentration of that incoming water? Well, it is the concentration of salt in tank 1, which is x over 10. And then times 2 to get the total amount coming in every minute from that tank. Concentration times rate at which it comes in. And then we must subtract off the rate at which salt leaves tank 2. Well, that is going to be the concentration in tank 2, which is y over the volume at time t, which is t. Remember, the volume of this tank changes over time. It's not always constant, it changes. And at time t, it's t. So this is the concentration of salt in tank 1, or 2, sorry. And then you need to multiply by the rate at which it leaves, but that's just 1. Okay, so what do we get for y prime? Y prime is x over 5 minus y over t. Okay, well, let me give myself any room here. So let's erase this a little bit. And go over here. Maybe zoom in a little bit, give ourselves a little bit of a chance. Okay, so let's just summarize what we just did here. Okay, x prime is equal to, there's no incoming salt, there's only outgoing salt, it's minus x over 5. And y prime, we just decided it was x over 5, or we calculated, minus y over t. Okay, now this looks a little bit daunting. This is unlike anything we've seen so far. It looks like we have coupled differential equations, because the rule for one function depends on the other function. The rule for y depends on x. So you get a taste for, you know, the complexity of this physical system. Although it turns out that this is not such a strong coupling in this problem. But this gives you a hint at what's coming next. The next couple chapters will be delving into these sorts of differential equations called systems of equations, in a more serious, you know, considering them in a more serious way. But for now, let's. This is not so serious because we can solve for x. X does not depend on y. The rule for x does not depend on y. So let's just consider this equation first. Okay, it's separable, so let's separate it. So let's solve the first equation for x. So we got 1 over x prime is equal to minus 1/5. Now to solve, we should integrate with respect to t, both sides. So the left side becomes an integral with respect to x, 1 over x dx. The right-hand side is just going to be minus antiderivative of 1/5 dt. So we'll get x is always going to be positive. It's the number of grams present. So we don't have to worry about x being negative. So we can just write this is the natural log of x. No absolute values required. On the other side, we just get minus 1/5 t plus some constant c, some number. And so we find that x itself is equal to some positive constant, c prime. It needs to be positive this time, no absolute value, funny business, e to the minus t over 5 for some c prime positive. All right, almost done here. Let's figure out what the constant is. So since the value of x at time 0, well, let's see, what is that? That is the number of grams of salt when we start in tank 1. And if we read up here, there's 2 grams of salt in tank 1. So this is 2. And it's not hard to see, you just plug in 0 in for t, that'll tell us that c prime is equal to 2. So x itself is equal to 2 e to the minus t over 5. Okay, so as I said, you know, this looks a little bit of a daunting kind of coupled equation where the rule for one of the unknown functions depends on the other one, but t is not so, or sorry, x is not coupled together with the y in that way. So we could just solve for x with no funny business. Now let's take a look at the equation for y. That now becomes something that I can write down only in terms of t and y, no more x's, because I just figured out a formula for x in terms of t. So y prime is equal to 2e to the minus t over 5 minus y over t, or if I want to write this, it'll turn out to be a linear equation. If I want to write this in a good way, let's write this as y prime plus 1 over t y is equal to 2e to the minus t over 5. All right, so now this is linear. No longer separable, it doesn't seem. So it's linear. So we have to use our knowledge of how to solve that, those types of equations. So let's do so. All right, so let's figure out what the integrating factor is. Let's zoom in, give ourselves a fighting chance to not have to erase anymore. All right, so the integrating factor, let's call it u. That's the e to the antiderivative 1 over t dt. So this will just be t. So if we take equation star, so if we multiply star by u, the equation becomes, the usual trick for linear equations happens. And what do we get? We get an equation where the left-hand side is now y times t prime, and the right-hand side is 2t e to the minus t over 5. Now we integrate, so yt is equal to 2 times antiderivative of t e to the minus t over 5 dt. And now we have to integrate by parts. And a little bit of work. Integrating by parts, where you differentiate the t and take the antiderivative of e to the minus t over 5, will tell us that this is equal to, let's see, minus 10 t plus 5 e to the minus t over 5, plus some constant c. All right, so it looks like I will have to do some mild erasing. That's okay. So wait, now let us use the fact that the tank starts empty. So y at time 0 is equal to 0. So if I plug in 0 in for t, I should get 0 out for y. Okay, so let's see what happens when we do that into this equation. So this equation becomes 0 is equal to, let's see, so the t is 0, so this is just becomes minus 50 times e to the 0, and then plus c, which is, well, it's just, we don't know what it is. So that tells us that c should be equal to 50. So if we divide through by t, we get that y itself is equal to, let's see, minus 10 t plus 5 over t e to the minus t over 5 plus 50 over t. So that's how many grams of salt are in tank 2 at time t. Notice, okay, so this looks a little bit fishy because you're dividing by t, and it's not clear that as t, like if t is 0, you get 0 out of this function. This is kind of a formal issue, technical issue. And notice that the fact that you have the 50t here and a kind of a minus 50t, albeit multiplied by this e there, when you take the limit as t goes to 0 from above, those things cancel out, and you indeed get just kind of this t times the e to the minus t over 5 at time 0, which is 0. Okay, so that's kind of a more complicated version of a tank problem. This one was like a 2-tank problem. Initially, it seemed like a coupled system, and later we'll consider tank problems where the two different tanks will affect one another. You could imagine the 2 tanks flowing into one another. That's a different scenario that we'll return to in the future. Okay, Good. So let's turn our attention to the next section. And this one will take a considerable amount of time, I would say. So this will contain a lot of information. Don't be surprised if you feel that way. So I'll try to break it down into a couple of more manageable parts, but a lot of content is in here. So we'll consider a lot of different first order differential equations that will fall into this form. And this kind of generalizes a lot of, I mean, basically everything we've seen so far. Well, let's take a look. Okay, so we're going to be looking at differential equations that take the following form. So it'll look like some function p of both the variable and unknown function y plus q times also a function of both times the derivative of y, all equals 0. So basically everything we've seen fits into this general form. This is actually extremely general form. Basically every first order equation will kind of fit into something of this form. Now we won't be able to solve everything that looks like this, but let's take a look at what we can do. There's not a special name for this form, by the way, but we'll have enough special names. All right. So as we know, often all the best we can do if we want to try to solve an equation is not get an explicit formula for it, but just an implicit formula for it. Something in this form. Some amalgamation of x's and y's, say, is equal to a constant. That's kind of the best we can do. Some equation that defines y implicitly in terms of x. Something like, the equation x squared plus y squared is equal to 1. That describes a circle of radius 1. But this defines, so this, I would say, defines y implicitly. And in fact, you can't actually, as this is a circle, you can't actually find a formula for y as it, well, I mean, you kind of can, but it's not y is not in general a function of x. The set of points that satisfy this equation is not the graph of a function. It fails the vertical line test. So you shouldn't necessarily even want to solve explicitly for y. Anyway, so this is often as good as we can do, find an equation like this. Here, in terms of the language that I'm introducing here, I'd be thinking of this as this, the capital F in this example would be like x squared plus y squared. Capital F, just some function of x's and y's. We know that something of this form, that thing equal constant, is as good as we can do. So you can kind of say, you could, downgrade our goal from trying to solve the equation star to just trying to figure out some capital F function of x and y, so that capital F is equal to a constant. That's kind of our goal. I shouldn't label that star. That's like a different thing. So that's our goal, roughly. Instead of directly solving for y, maybe the best we can do is try to come up with a capital F so that we know that capital F is constant. We'll see what I mean by this much more explicitly. So we're kind of thinking, okay, this is kind of the best we're doing. This equation here treats x and y kind of on the same foot. Like this equation does not really say that y is more important than x. It implicitly defines y in terms of x, but you could switch that around. It also implicitly defines x in terms of y. So x and y are kind of at the same, treated like the same level in this perspective. And we'll adopt this perspective. We'll think of x's and y's kind of on the same footing, even though we know we're trying to think of y as a function of x, but in this perspective, which we should zoom out. Let's think of them kind of on the equal footing, and then it kind of makes sense to multiply both sides by dx, kind of like what we did with the separable equations. We had that integration with the u substitution that turned an integral with respect to t into an integral with respect to y. Similar things going on here. You know, where heuristically you're canceling out the dt with the dt in the denominator from a dy dt. It's a similar idea here. Now this can be made rigorous in a number of different ways. One way you could make this rigorous is to think of the resulting equation, what you get when you multiply star by dx everywhere, as an equation for what's called a differential form. You know, here I call this differential form omega, p dx plus q dy. And I won't always be writing p of x and y, q of x and y, just write p and q. But this is simple. Right now we just are abstractly treating dx and dy as some symbols. We don't really have too much of a meaning for them, some vaguely infinitesimal things. But it's not so important to know all of their formal properties. You know, I'm telling you that this left-hand side can be regarded as a differential form, but we're not going to really need any properties of differential forms or anything like that. If you look that up on Wikipedia or something, you'll be led down a very different rabbit hole than what we're doing right now. Anyway, so this is what we're trying to, we're going to be trying to think of this equation as an equation for this differential form, object like this. Let me just tell you maybe a little bit more. You've seen these objects before, these differential forms, but they were probably not called that. Maybe they were, depending on what class you took. But from vector calculus, let us recall, if you have a function of two variables, as opposed to just one, when you have a function of two variables, like capital F of x and y, there's a couple different notions of what is a derivative of capital F. So first of all, you have the partial derivatives. You could take your expression for f, think of y as constant, take a derivative with respect to x. That would be the x derivative, treating y as constant, taking a derivative with respect to x. Or you could do the other way around. You think of x as constant in your expression and take the derivative with respect to y. So those are notions of derivative. You also have the notion of the gradient, which is made up of the partial derivatives, but is, in terms of thinking, a different quantity altogether. The gradient of a function of two variables is a vector. The first input, the first coordinate of the vector is the x derivative, the second, the y derivative. So, you know, these are all going to contain the same information, but they're different objects, and you should think of them kind of differently. And then the other one that was probably mentioned is, or maybe not, depending on the class again, either the total derivative or the differential of f. Again, just made up of the partial derivatives, but organized in a different way. So it's usually denoted df instead of this triangle, nabla f. It's df, and it is the differential form looking thing that we talked about just a second ago. It is partial derivative with respect to x, dx, plus partial derivative of y, partial derivative with respect to y, dy. So we've seen these things before. It's a way of organizing the derivative of a function of two variables. Okay, so basic thing to notice, if f of x and y is equal to constant, you know, just kind of like the goal that we have for our equation, you know, in terms of solving our equation, that's our goal, is to get something like this. Then if you take the differential of both sides, you find that df is equal to 0. So partial derivative with respect to f dx is equal to, or sorry, you know, plus y derivative of f dy is equal to 0. So this is you know, kind of relevance to the problem at hand. You know, this total derivative looks a little bit like the differential form in the equation that we're trying to solve, and it will kind of come from the sort of goal that we're trying to get to. Anyway, some other nomenclature. the set of points that satisfy an equation f of x, y is equal to a constant, the points x and y in the plane that satisfy that equation, they're called the integral curves of the equation df is equal to 0. Okay, so they'll be kind of the curves that represents solutions to our differential equations. So for instance, if you look at this differential equation, x dx plus y dy is equal to 0, this left-hand side will be equal to df, where f is equal to x squared plus y squared. So that, to see that, just note, partial derivative with respect to x is just 2x, because y is thought of as constant, so its derivative with respect to x is 0, and dy of f is equal to 2y, and so df, which should be constant because it's equal to, f is equal to 1, so derivative of 1 is 0. So df is equal to 0. That can be written as 2x dx plus 2y dy is equal to 0. Divide both sides by 2, you obtain this differential equation. X dx plus y dy is equal to 0. So in kind of a roundabout way, we just solved that differential equation. X dx plus y dy is equal to 0. If x and y solve that equation, then x squared plus y squared is equal to a constant. And the integral curve is just one of them in this case, is the unit circle. As we just discussed, the set of points solving that equation, it's like the set of points which are distance 0 from the origin, or sorry, distance 1 from the origin, that describes the circle. Okay, so that's kind of a roundabout way, the first solution. So the first solving of a differential equation in this form. All right, I've readjusted that too. Okay. As I was mentioning, we just did a kind of reverse version of what we wanted to do. So our goal is to, instead of deducing an equation from a function of two variables, we want to come up with that function of two variables from a differential equation. So this is kind of the first hint of how we're going to do this, because the differential of a function of two variables is the type of equation we're looking at, or has the form of the equation we're looking at. Okay, so here is the general strategy. So to solve this differential equation, which is written in kind of a funny way, this differential form way, p dx plus q dy is equal to 0. We're going to want to find the capital F of x and y so that its differential is the left-hand side of the equation. Or in other words, that partial derivative of f dx is equal to p, and y derivative is equal to q. So if we do so, then this equation here, f of xy is equal to a constant, will implicitly define the solution of the differential equation. A little bit of a roundabout idea, well, and also not very practical. I haven't told you how to do this, but this is what we want to do. Given the p and the q, we want to come up with an f so that x derivative of f is p, y derivative of f is q. Then f being constant will define the solution y. One thing, which is a roadblock to that, never mind how to do it, but it's not even always possible. So not every differential form, like so, p dx plus q dy, is the differential of a function of two variables. So there, I mean, there's an obstruction. This is not always possible. So you shouldn't, I shouldn't have even tried to give you a way of doing it, because you can't always do it. In fact, there's a special name for differential forms for which this is possible. They're called exact. So a differential form, like we've been talking about, e dx plus q dy, it's called exact if it is the differential of a function of two variables. So if this can be written as the total differential of a function of two variables. All right, special name, exact. So here's a situation where I'll tell you right off the bat that this is exact. I'm just not giving myself very much room here. So I'll tell you right off the bat, the left-hand side of this equation is exact, so it will be possible to write it as d of a function of two variables. So let's try and do it for this example. So let's see. We want a function of two variables, capital F of x, y, so that two equations are satisfied. So that on one hand, I want the x derivative of f to be equal to x, the p function in this problem, and I want the y derivative of f to be equal to y squared, because the q in this problem is y squared. If these two equations are satisfied, then the total differential of whatever function I come up with will be the left-hand side, and so that function being constant will be an implicit definition of y in terms of x. Okay, so let's see. Let's take a look. This first equation says derivative with respect to x of f is x itself. So we want to solve for f. It's trapped behind the derivative with respect to x. We should integrate with respect to x. So f itself from this equation will be equal to the integral, this is of x and y. Might not always write that implicit. Is equal to the antiderivative of the right-hand side with respect to x. Okay, just integration undoes differentiation, but we have to be a little bit careful because these are partial derivatives. Partial, or and integrals with respect to a specific variable. Integrating x with respect to x is just 1/2 x squared. Now, you got to remember, I'm integrating a function of two variables with respect to x. So a constant is just a constant in x. It could depend on y. So it could depend on y, this constant. I'll call it phi. It might be a function of y. So this, this is constant in x from integration. Okay, so haven't quite found a formula for f yet. I still got this phi. I don't know what phi is. I don't know. No reason to choose phi either. Just that's what the book does. Some unknown function of y. Well, it makes sense. We haven't used that other piece of information yet. So let's look at the other equation. This is not a minus sign. From this, we know that when we take a y derivative of f, we should get y squared. So, I got a formula for f, not quite complete, but I have a formula for it. So when I take the y derivative of that, I should get y squared. So let's take a y derivative of 1/2 x squared plus phi of y. That should be equal to y squared. On the other hand, when I take a y derivative, that x stuff goes away. That's 0. Doesn't depend on y at all. And then I'll just get a phi prime of y. It's the y derivative of phi. I don't know anything about that. I just write down phi prime. That should be equal to y squared. Well, I want to figure out what phi is because I want to figure out what f is. So I'm looking at this equation. The phi is trapped behind the derivative. I need to integrate that to figure out what phi is. So phi itself is equal to just 1/3 y cubed plus some constant of integration that you don't really even need to write because there's going to be that ambiguity anyway. Anyways, we have done what we set out to do. We have together found a formula for capital F. So capital F xy is equal to, okay, as you got that 1/2 x squared, and then plus c. We just figure out what phi is. That is 1/3 y cubed. And as I said, the constant is not material in this situation. Anyway, so this is what f is. It's just a function whose total derivative is equal to that left-hand side. So this thing being constant, well, let me just actually write it down. This expression being constant is the implicit definition of y in terms of x. So 1/2 x squared plus 1/3 y cubed equal to a constant. Let's just call it c. This is the implicit formula for y. Actually, in this case, we can solve for y. It's going to be a function of x, but and there's a reason for that. We'll see later. But we accomplished our task. Okay, so that is how that process of trying to figure out this perspective of solving this differential equation. So we just wrote down what it is that different color. We just wrote down what it is that we want. Well, we want the x derivative of this unknown function f, capital F, to be p, in this case x. We want the y derivative to be q, in this case y squared. And then we just followed our nose. We tried to integrate one of the equations that left us with this unknown function of the other variable. And then to figure out that unknown function, we took the derivative of that expression, and then we used the other equation that we hadn't used yet to figure out what that should be equal to, and solved for the unknown constant of integration, in this case phi of y. That tells you a formula for f. So that thing being constant is basically the solution to the differential equation. The story ends here. Unless someone asks you specifically for you to solve for y, which is not always possible. Okay, so that's how this is going to work out in practice. Well, let's get a little bit more theory here. We mentioned, okay, this procedure that I just outlined, it's definitely not going to work if what we're trying to accomplish is impossible. So it's not going to work out when the left-hand side of the differential equation is not exact, when there's an obstruction to writing it as the differential of a function. Here's a fact that will make everything a bit more clear. Here's how to check when p dx plus q dy is exact or not, whether that method I just described in the previous problem will work or not. You just have to figure this out. If the derivative of p with respect to y is equal to the derivative of x, or sorry, derivative of q with respect to x. So you take the thing in front of the dx, you take a y derivative, the other variable, derivative of it, and you check, is that equal to the x derivative of q? It's the opposite. You take the derivative with respect to the opposite variable to the little symbol that it's attached to. Okay. Why? Why is this true? Well, notice it's kind of interesting. Yeah, I mean, this is a kind of interesting question. When can you write a symbol like this as the differential of a single function? So this is actually a little bit deep. It's probably the deepest thing we've seen so far in this class. Let me just give you a hint to what's going on here. Well, notice, so if this differential form were exact, so if, let's write the same thing again, if this is exact, then let's see, p will be equal to the partial derivative of f with respect to x, and q will be the y derivative of f. That's just what it means to be, exact. There's a function f that makes this happen. And now notice that dy of p, well, that'll be dy of dx of f. You just take the y derivative of that equation a little bit above it. Likewise, dx of q is equal to dy dx of f. And now, you might remember this from vector calculus, but it's kind of interesting thing that's not totally obvious, but the order of differentiation does not matter for a nice, smooth, function whose derivatives are continuous. The order of differentiation does not affect the outcome. So if you first take the x derivative, then the y derivative, that's the same as doing that vice versa. Taking the formula for f, then taking the y derivative, and then after that, taking the x derivative. Reversing the order of differentiation does not affect the outcome for most functions. So these are the same. Maybe the key word that might have been told to you at the time was derivatives commute, partial derivatives. Commute, which is just to say the order is immaterial. Anyway, so that's where this condition is coming from, because this condition that dyp is equal to dxq is the same thing as saying that, well, at least it is saying that, or at least if it were exact, then it's clear that why this equation should be true. It's just the fact that partial derivatives commute. The other way around is not at all obvious. How you can come up with a function f just by knowing this. That's kind of an intriguing part of this fact. We won't go into that right now. Okay, so let's just give a quick overview of the method. So if you have an exact differential equation in this form, p dx plus q dy, where you know the left-hand side is exact, then you want to come up with the capital F, whose total differential is the left-hand side. To do that, you could integrate p with respect to x, and then remember that you're integrating with respect to x, so the integration constant may depend on y. So F will have this form. By the way, you could also do, you could say that f of x, y is equal to antiderivative of q with respect to y plus some constant of integration that will depend on the other variable x. So, either or is fine. One integral might seem to be easier to compute than the other. This is usually not a useful, regardless. So you have this expression for capital F. You compute one of the integrals with respect to one of the variables. And then you have this other function of the other variable that you don't know. So the next step is to determine what that function is by looking at the other equation. dy of f is equal to q. So if you followed this other track where you integrated the other equation, then you would, of course, look at the equation dx of f is equal to p to figure out what the other constant would be from that other train of thought. Okay, then once you figure that out, then you can just write down the expression f, or the equation f of xy is equal to constant, because you will at this point have determined a formula for f up to a constant, but this is going to be equal to some constant that you don't know anyway. So you don't need to keep track of that constant all the way through. The constant will just come through at the very end. Okay, so that's the skinny for when you're looking at an exact differential equation. So let's try and do this in practice. So we got an equation like this, 2x plus y plus x minus 6y times y prime is 0. Well, notice, well, this isn't in the differential form language yet. To convert it, we'll just notice that, okay, y prime is dy dx. And then we get the differential form version by, formally multiplying through by dx. It's not legitimate, but it's just another perspective on the equation. Anyways, and we get 2x plus y dx plus x minus 6y dy is equal to 0. Now it's in the form that we're familiar with in the context of this section. All right. So let's do our business. Maybe we won't need too much extra room, but okay, so just to be clear, this is what I'm thinking of as P, and this thing over here, this is what I'm thinking of as Q. All right, so let's take a look at one of them. Let's just write down, actually, here's a good idea. Let's write down the two equations we know that F needs to satisfy. So derivative with respect to x should be 2x plus y. The y derivative should be x minus 6y. All right. Oh, by the way, we know this is going to be, I should have said this before, but we know this is exact, since if you take the y derivative, so partial y of p, that's equal to just 1. And you get the same thing when you take the x derivative of q. Partial x of q is also 1, because those are the only two things that depend on the other variable. Okay, so we know this is exact, so we know that the scheme that we're about to embark on will work. So we know we should be looking for, we seek f of two variables so that these two equations are solved. Okay, now let's look at one of them, doesn't matter which one. Let's take a look at the first one, integrate it with respect to x, see what happens. So this first one tells us that f of xy is equal to antiderivative of 2x plus y dx. Very important to remember what variable you're integrating with respect to. And let's see, what is this? We don't have to add the phi at this point. I just did that in the instructions in the last page, just to make sure no one forgets it. Okay, so we're integrating with respect to x. Let's see what we get. Okay, we get x squared from that first term, and then integrating y with respect to x. It's like integrating a constant. That'll just be y times x itself. And then, of course, plus that constant in x, which might depend on y. Okay, so this is what f is. Now, we need to look at that other equation. Bring that down, which says that when I take the y derivative of this expression that we just found in green here, we should get x minus 6y. So let's take the y derivative of that green stuff. So we get 0 from the first part, and then taking y derivative there, we just get x, and then we get plus derivative of phi, which is just phi prime. We want to figure out what this is. On the right-hand side, we just have x minus 6y. Okay, so the x's cancel. Just subtract both of them, subtract x from both sides, they go away. So phi prime is just equal to minus 6y. Figure out what phi is, we just need to integrate. So phi itself is just the antiderivative of minus 6y. That is probably minus, it's definitely minus 3y squared. So we just figured out what f is. Capital F of xy is going to be x squared plus yx minus 3y squared. So what is the equation which implicitly defines y in terms of x? Well, it is, keep on writing that. It is x squared plus yx minus 3y squared is equal to a constant. And as usual, let's just write c for some c. if you're interested, I believe the curve, the integral curves of the differential equation will be hyperboloids that are shifted a little bit. Anyway, this is the end of the problem. I give myself more space on this one. All right, so what can we do in the situation where the equation happens to not be exact, where we are in the situation where we can't hope to find a capital F so that the left-hand side of the equation is df? We've solved other differential equations that, and I mentioned that everything we've done so far can be phrased in this form. We've solved other differential equations. They can be written in this form. And those other equations, they weren't all exact. So we know this is not the end of the road if it's not exact. We know that things can be done. So what happens next in this section, we're going to go through a number of different scenarios where you can still do something, even though the equation is not exact. And it might be a little bit confusing, but there's really going to be 3 other scenarios that we entertain in this direction. Okay. So first of all, to kind of a piece of theory to kind of center our discussion, here's another interesting fact that's not totally obvious. So if you have some differential form like this, p dx plus q dy, it might not be exact, but you can say there's always going to be some function that you can multiply this by so that the result is exact. So up to multiplication by some function, everything is exact. And precisely, I mean, there is some function, call it mu of x and y, so that if you multiply the form by that function, so now the form becomes mu p dx plus mu q dy, that will be exact. It doesn't tell you how to come up with the function. That's the hard part. But such a function will exist. And once you suppose you could always find the integrating factor, then you would be able to always transverse or translate inexact differential equation in terms of an exact one, and then run that procedure we just described. This mu is called, as a name, it's called an integrating factor, just like the u. The u, if you organize your thoughts correctly, the u from before, from the linear equations, is an example of a mu. And it's not a coincidence that when you solve the linear equations, you get the integrating factor, you multiply both sides by that integrating factor, and then the left-hand side turns out to be a derivative. And what we're doing here, we're trying to write the left-hand side as the total derivative of one function. That was actually what we were doing in that section, this business. Anyway, the mu is very hard to find. It's kind of remarkable that it exists. That's not obvious from our perspective at all. But unfortunately, it's basically always very hard to find. It's basically solving, to find mu, it's like solving a differential equation for a function of not one variable, like what we've been talking about so far. So far, we've just thought of y as a function of x, trying to find a formula for y in terms of x. If you try and write down what it means to find such a mu, this will actually be an equation for mu that depends on both x and y. There's such a thing where you're trying to find, you have a differential equation for a function of multiple variables. This is called a partial differential equation, which is a different sort of question, sort of a class almost, except we'll be covering some aspects of partial differential equations in this class in the last 3-4 weeks or so. But anyways, it's a different world almost, and we don't have any techniques so far for solving them. And they're hard to solve. They're not, you wouldn't expect to be able to solve them. All right. Essentially, because not only are you supposed to solve it, you're supposed to find a formula for it, and then use that formula to plug into that step-by-step procedure we just talked about. Anyways, it'll be hard. So here's something where the problem is more tractable. When it so happens that mu, the integrating factor, only depends on one of x or y. When that is the case, then things become more tractable. So let me give you another fact, which is not as deep as the other ones, but let me say it anyway. So if you try to figure out how to take this inexact problem, px, p dx plus q dy equals 0, where that left-hand side is not the differential of a function, where it fails that commutativity of the partial derivatives, and you try to find the integrating factor. Well, if this quantity, h, we'll name it, it's a name for something, if this thing h, which is 1 over q times the quantity y derivative of p minus x derivative of q, if that thing only depends on one of the variables, namely x, then mu will only depend on x, which will considerably simplify the situation. In this case, if this quantity, this kind of mysterious quantity h, 1 over q, y derivative of p minus x derivative of q, depends only on x, then you'll be able to solve for mu. It'll be given by the solution to this linear, well, separable and linear differential equation. X derivative of mu is equal to h mu. So that will allow you to figure out this. What I'm trying to describe here is a situation where finding this integrating factor is tractable. So if it only depends on one variable, say x, then this quantity will only depend on x. And in fact, when it only depends on x, then you'll be able to solve for mu according to this equation. Now, where does this come from? So we'll do an example of how to do this in a second. But where does this come from? It's not so mysterious. There's only one meaning for mu. It's that when you multiply the form by mu, it becomes exact. So let me just explain, where did all these mysterious quantities come from? Well, let's take a look. Okay, so suppose you have some function mu so that when you multiply the form by it, it becomes exact. So suppose mu times p dx plus q, or mu times q dy is exact. Then, what does that mean? That means, according to that fact that we saw from before, that the y derivative of mu p is equal to the x derivative of mu q. Remember that fact from before? If you take the x derivative of the thing over here, and that's equal to the y derivative of the thing on the left, that's the same thing as being exact. So I just wrote that down. Now let's write down what happens if mu is independent of y. So let's assume well, that the y derivative of mu is 0. In other words, mu does not depend on y. Then this equation becomes, let's see, so then the left-hand side is just mu times partial derivative of p with respect to y. The right-hand side, you got to use the product rule because it depends on x. So you get a derivative with respect to x of mu times p plus mu times x derivative of q. So let's solve for let's write this. So this is a differential equation for mu. Let's write it down. Let's move some symbols around. Okay, so if I subtract off this mu dx from both sides, I'll get a mu, dxq. Mu times partial y p minus partial xq is equal to, partial x mu times p. Or, in other words, 1 over p, I guess, mu times 1 over p times dyp minus dxq is equal to let me just write it as, how about mu prime? No ambiguity about what partial derivative I'm talking about because mu only depends on x. Okay, so that is exactly this. I just used the shorthand h because this quantity here next to the mu, this is h. So that's where this quantity comes from. That's why if it depends only on one variable, then mu only depends on one variable, namely x. You can imagine a similar story if mu only depended on y. You would do the same calculation, except when you encountered the x derivative of mu, you would ignore it because that would be 0. Right, so this is the explanation of this fact and why these quantities pop up. All right. What else can we do when all right. Let's try to work through this example here. I didn't typeset it, but imagine as if it were. All right, this is going to be a situation where this is not exact, this thing here, yet we'll be able to figure out the integrating factor. All right, so this is not exact because notice that the y derivative, partial y of this thing, is equal to just x, and the x derivative here of this thing, writing them as boxes, is not x. It's 2x minus y, different than just x. So this is not exact. Now, the best thing you can hope for is that it will be not so bad to try and find the integrating factor that makes this exact, the mu, so that when you multiply this left-hand side by mu, it becomes exact. Well, let's try and run through, what we were just told, to think about this quantity h, the 1 over q times this business here. So let's compute. If this, well, okay, yeah, let's compute this h quantity, x squared minus xy times y derivative of that, x minus the x derivative of q, so 2x minus y. Okay, so let's see what we got here. We got a little bit of cancellation here. We got a x with a minus sign, and then plus y over and then in the bottom, we could factor out an x. We get x times x minus y. Well, these cancel, up to the top is negative x minus y. So these can cancel, and this becomes minus 1 over x. And notice this only depends on x, no y's. So we're in business. Now, from the fact that we just learned, this means that the integrating factor will be a function of just one variable, and it will not be so unmanageable. So now we know the integrating factor mu will satisfy this its derivative So it'll only depend on x, and its derivative will be equal to h times mu. So it'll satisfy, by the way, it's only a function of x, and mu prime will be equal to minus 1 over x mu. Or in other words, all right, so we solved this equation. Divided by mu, 1 over mu prime is equal to minus 1 over x. Integrate both sides with respect to x, do our usual separable thing. On the left-hand side here, we'll get natural log of mu. On the right-hand side, we'll get minus natural log of x, plus a constant, which will be irrelevant. We just want to find a solution to this differential equation, not all of them. We just want to find some integrating factor, not every possible integrating factor. There could be multiple. So let's just choose the one that has integrating constant 0 for simplicity. All right, so trying to figure out what mu is now. So we exponentiate both sides. We get mu is equal to 1 over x. If you integrate minus natural log, or sorry, exponentiate minus natural log. This is what we get. So we multiply our equation by 1 over x. What do we get? Well, we get y minus 1 over x dx plus dividing everything by x, we just get x minus y dy equals 0. Now let's notice this thing here. So let's just confirm that we have done what this is supposed to have done, which is made the left-hand side exact. So let's take the y derivative of the left-hand side. We get, partial y of this thing is 1. The x derivative of the right-hand side, but the right-hand thing on the left-hand side is partial x of this thing is also 1. So this is exact now. All right. And then we'll leave the rest of the solution of the problem at this point as an exercise. At this point now it becomes like the previous problem where you want to find the capital F. You just integrate, solve for that integrating constant phi of y. Very similar to the last one. Okay, so let's move on. So again, in this part of the section, we're trying to go through and kind of answer the question, what what can be said if the equation fails to be exact? So we just saw kind of very general answer, which is, well, if it fails to be exact, actually, turns out you can always find a function so that when you multiply the equation by that, it becomes exact. This is not always possible or not always easy to compute this thing. We just saw when it is possible to compute that thing when it only depends on one variable or one of x or y. What else can we do? Here's a fact. This is kind of just a one-off simple thing, but if p and q each only depend on one of the two variables, then usually I've been calling x a variable, y is the unknown function. But in this section, I'll be kind of treating them on equal footing, so I'll kind of refer to them both as variables. Anyways, if both p and q only depend on one, either x or y, then the equation will be separable. It'll look like p of, say, let's suppose p depends on x and q depends on only y. Y prime is equal to 0. And this will indeed be separable. You could write this as q of y prime is equal to minus p of x. Other situations where, say, they both depend only on x, then you might have to divide both sides by q of x to separate the variables. Nevertheless, in any of those four possibilities of p and q both depend on x or y or xy and then yx, they'll all be separable in all those scenarios. So that's just something to note. So even if the equation might not be exact, it could be separable, in which case you know how to solve the equation. You separate, integrate, and solve. Sometimes this might not be immediately obvious that it's separable. For instance, let's take a look at this equation. Let's see, how about we divide both sides by y. So then this becomes x to the 3/2 dx plus, I'm dividing everything by y now, so this is y squared root x dy is equal to 0. And let's divide through by square root of x. So then this becomes x dx plus y squared dy is equal to 0. And this is indeed separable. Also, it will be exact. This is also exact. So you could use any of the methods that you could either think of it as exact and then use our, technique that we described to solve exact equations, or you could think of it as separable. Probably I would suggest doing that because separable things are easier. You just need to integrate and not think about auxiliary function or anything like that. But it turns out you can solve this one without too much work. That's just something to keep in mind. You might be staring at a separable equation. Okay, what else? What else can you do? Well, here's another scenario. So we're kind of listing off scenarios in which the equation is not exact, yet you can still do something. So here's another interesting situation. Suppose, okay, so let's take a step back here. Let's make the following definition. If you have a function of two variables, say g of x and y, this is said to be homogeneous of degree n. Homogeneous means like sameness. And in this use of the word, it means like the sameness of how it treats the two variables. So saying that it's homogeneous is kind of heuristically saying x and y are on the same footing in some sense, in the following sense. If you multiply the x coordinate by t and the y coordinate by t, if you scale those two inputs in the same amount, then t to the n pops out. So in other words, g of tx comma ty is the same as t to the nth power times g of xy. So, for example, g xy, this is just like x to the, 5 plus x times y to the 4. This will be homogeneous of degree 4. Note, if you multiply both of the inputs by the same factor, t, then you get, okay, t to the 5th comes out of that first thing. And then you'll get a tx times t to the 4th, y to the 4th. So t to the 5th factors out of everything. And so this whole thing is equal to t to the 5th times g of x comma y. So this is homogeneous with degree 5. This is the kind of trying to capture. Now, a differential equation is said to be homogeneous if it looks like this. Px plus pdx plus qdy, like we've been studying. And both p and q are homogeneous of the same degree. So if they're both, well, I'll give you an example of one in a second, but if they're both homogeneous of the same degree, then it'll turn out that, well, we give a name to it. We call the equation homogeneous. This is kind of a slightly different meaning than we use the term homogeneous and non-homogeneous in the context of linear equations. It's slightly different. I mean, it's deep down, it's the same notion because both have the same root word, but technically different. Okay, here is the good news. If you have a homogeneous differential equation like this, then it turns out you can always solve them. Well, I mean, there's a simple way of solving them. If you introduce this new auxiliary function of x, if you decide to say, well, I'm not going to think of this as y as a function of x anymore, I'm going to introduce a new function, v, which is y divided by x. I'm going to think of that as the main thing I'm trying to solve for. I guess kind of like a change of variables, or just rewriting the equations in terms of a new function. Let's fix, let's hone in on this new function, y divided by x. Turns out this will be a good thing to do. If you make this substitution, if you declare v to be y over x, and then try to rewrite equation star in terms of only v's and x's now. So totally try to do away with y's, replace them only with v's and x's. Then this equation will turn out to be separable. Very interesting. And then, so it's a separable equation, not in terms of y anymore, but in terms of v and x's. But it'll be separable, and you'll be able to solve it in the usual way. Totally not an obvious thing to do right off the bat. Let me tell you why this will work. So, just to give you a hint of why would one make this substitution? Well, notice that if you make this substitution, then y is the same as x times v. Okay, now you'll just multiply both sides of that definition by x. Now notice that if you consider p and q, they're both functions of x and y. So with this substitution, y is this x times v. So instead of p of xy, it'll be p of xv. And by assumption, p is going to be homogeneous of some degree, say n. So this is like you have scaled 1 by x and v by x. So think of t as x in this case. And the homogeneous condition will tell you that p of x comma xv is just equal to x to whatever order or degree of homogeneity it is, times p of 1 comma v. So in essence, this thing, the thing in front of the dx basically only depends on v. So only depends on v. So which reveals its separable nature. And the same thing will happen with q. You'll divide through by x to the n and you'll be in business. So that is the reason why the substitution is a good thing to do. The homogeneous property will basically allow you to write the p and the q as more or less functions of one variable. The other one will kind of fade away after you make this change. Let's see how this works in practice. So here's a situation where these are both very simple homogeneous quantities here. These are both homogeneous of degree just 1. Okay. So what should we do? Well, we were told we should do the substitution. V is equal to y over x. So now we want to redo everything in terms of, rewrite the equation just in terms of v and x's. Well, let's put this in a little bit of a easier to understand form. So this is x plus y plus x minus y times y prime is equal to 0. Let's not write it in the differential form way. Let's write it this way. And let's see how the derivative of v and the derivative of y relate to one another. So maybe let's write this as xv is equal to y and take a derivative with respect to x. So taking derivative with respect to x here, I get v plus xv prime is equal to y prime. So let's put these facts together to rewrite the equation only in terms of v and x. All right, so I'm looking at the differential equation here, and I'm just going to write it down, but replace all the y's with their corresponding v expressions. Okay, so I got x plus y, which is xv, plus x minus y, which is xv, times y prime, which is v plus xv prime. That's supposed to be 0. All right, now let's simplify things a bit. It looks like we have a common factor of x, so we can divide everything by x. We get 1 plus v plus 1 minus v times v plus xv prime is equal to 0. Now let's divide everything by 1 minus v. So we got 1 plus v over 1 minus v plus v plus xv prime is equal to 0. Or in other words, v prime itself is equal to 1 over x. Doing a little bit of arithmetic here, negative sign, and then we just get v plus 1 plus v over 1 minus v, which is now, well, almost separated. Now we have to divide both sides by this expression of v. So before we do that, maybe let's simplify the expression a little bit, 1 over x. Let's combine these two things here. So this will be a v minus v squared plus 1 plus v over 1 minus v. All right, so this is v prime is equal to 1 over x, the minus sign. We got, let's do a plus sign, so we'll have a v squared minus 2v minus 1 all over 1 minus v. We get 1 minus v over v squared minus 2v minus 1. Let's integrate. So integral with respect to v over here and antiderivative 1 over x with respect to x over there. All right, now, I'll zoom in maybe. Let's do a u substitution. So let u be, we just want to compute this left-hand side integral. That's the only not obvious thing here. So let's let this be the denominator, v squared minus 2v minus 1. That means that du is going to be 2v minus 2 dv. Or in other words, 1/2 du is equal to I guess minus 1 minus v dv. So that allows us to compute the left-hand side. This will be the antiderivative of 1/2, just 1 over u du. On the right-hand side, antiderivative 1 over x dx. Oh yeah, I should have a minus sign there. So what do we have? Left-hand side is minus 1/2 log, or, natural log of u, which is v squared minus 2v minus 1. The right-hand side is natural log of x. So we might need some more space. 1 over the square root of v squared minus 2v minus 1 is equal to x times some constant c, or some c. And then let's write it in terms of y itself. Remember, v is y over x, so we have 1 over the square root of y squared over x squared minus 2y over x minus 1 is equal to cx for any constant c. All right, and let's end it there. That's not the prettiest looking solution, but making this important substitution, v is equal to y over x. Writing the equation, it'll always turn into a separable equation. And then you just integrate to solve the separable equation. In this case, there's a little bit involved, but it's straightforward. All right. Very good. Now let's take a bit of a step back and make some remarks about what we're doing. As I said before, we kind of jumped right into computing solutions to differential equations, learning some different techniques for solving them in practice. But there are some fundamental questions like, what are we doing? Do we even know that these have solutions? We're computing them, but do we know we should be? Or, or did that make any sense that we were supposed, should we have, is that our goal? Should that be our goal? What about other questions like, if you have some very general looking differential equation, first order differential equation, suppose we specify some initial value problem. This quantity is 0, some differential equation. That's just, this notation is just shorthand for any general first order differential equation. And then, some initial condition y of 0 is, 5 or something. Does this problem have a solution? If so, is it unique? It could be that somehow when we were solving, when we learned all these methods for solving differential equations, maybe we were missing some solutions. Or maybe, when we were doing the tanks filled with water, maybe there were some solutions that we should have been paying attention to that we ignored. Or perhaps there was that solution that we came up with was nonsense. It was not nonsense. What we were doing, everything we did made sense, but there's some underlying questions. Okay, so let's take a look at the following example. We've kind of encountered a little bit, a taste of it at least. Let's take a look at this differential equation. Very simple differential equation. Y prime is equal to y over x. Now, right off the bat, if you're thinking about what could go wrong, you're probably looking at that divided by x, and you're thinking something fishy might be going on when x is 0, and you would be correct. But let's see exactly what goes wrong, or what is fishy. Okay, so it's a nice simple equation. So let's look at this initial value problem and try and solve it. Nice simple equation, definitely separable. So what do we get? We get 1 over y, y prime is equal to 1 over x. So do our usual separable thing, integrate both sides with respect to x, get integral 1 over y. dy is equal to antiderivative 1 over x dx. So we get natural log of absolute value of y is equal to natural log of absolute value of x plus some constant, or any constant. We're going to have to pay attention here because this is a delicate issue that we're trying to investigate. So, let's be careful with the absolute value signs in our thinking here. So here, this constant c can be any number, for any number c. Okay, now we try to solve for y. Exponentiate both sides. We get absolute value of y is equal to c prime, absolute value of x, for any positive c prime. Okay, so y itself is equal to plus or minus c prime absolute value of x for any constant, for any positive constant c prime. Okay, but there's something a little bit weird going on. There's like two ambiguities of sign. There's the ambiguity of sign coming from the absolute value of y, and then the one from the absolute value of x. And this is going to be kind of the source of a little bit of the confusion. Okay, so let's just take a look at the, on the fundamental level, any of the following are going to be solving well, let me not use that bracket. So, y equals c prime times x, and y equals, c prime minus x. These are all solving the equation. Kind of the same thing. Anyways, they all solve the equation. So let's take a look. I want y at time 1 to be equal to 1. So since y at 1 is equal to 1, what does that mean for the constant? Well, that tells us that c prime has to be 1, and y should be equal to plus or minus x. Well, actually, maybe I don't like what I just did. Okay, so let's take a look at what actually is solving this equation. So here's the main issue. Let's take a look at the function y is just equal to x. Well, that satisfies the problem. Y at 1 is equal to 1. And it's of the form down here that we know that the solution should be in. So y equals x will be a genuine solution to this differential equation with this initial value condition. But here's another one. Here's another solution. What if I was minus x before 0 and then x afterwards? So y just equals the absolute value of x. This also solves the initial value problem. Not only does it solve the equation, remember the equation is not actual, the equation doesn't say anything at all at time 0. The right-hand side is not defined. So the equation says nothing at time 0. And this satisfies the equation at all other times. By time, I mean value of x. Anyway, this is also a solution. But let me tell you some more. There's going to be infinitely many solutions. So also, even worse, any function, I won't give you a formula for it since it's piecewise defined, a little bit cumbersome to explain, but anything that is a line that passes through 0 and then equals x after the value x equals 0. So any line like that, that'll be a solution. Let's draw another one in a different color. A function that says maybe has negative slope and then it equals x after there, or you can see where this is going. Anything that is a line that meets 0 and then continues on as x after x equals 0 will solve this initial value problem. So big issue here. So we get infinitely many solutions to the initial value problem. Big time, not unique. Solution is not unique. Okay. Now, and this is kind of a theme, whenever you have issues with uniqueness, you'll also have issues with existence. So let's record something that we learned from the last tile or whatever, that y is equal to c prime absolute value of x. Well, I mean, that is, well, let me just say it this way. Absolute value of y is equal to c prime times the absolute value of x for any positive c prime. Okay, let's take a look at this initial value problem. Same differential equation, so this, what we said here is still true, but now we want the value of y at time 0 to be equal to 1. Well, this is never possible. So notice that for any choice of c, y at time 0 always has to be 0, because the absolute value of 0 is 0. So y has to be 0 when x is 0. So there's no way. So this will never be satisfied. Never the case for any solution of the differential equation. You're never going to be able to make it equal to anything other than 0 at time 0. So this differential equation had a problem at time 0. The right-hand side is kind of no good at time 0. And this led to both an existence problem and a uniqueness problem. They usually always go together. In fact, I can't think of an example where they don't. Not a simple one. So this is kind of what we're up against. Here's a fact that kind of articulates what we were just saying. Okay, suppose we're looking at this problem, the sort of problems that we've been studying in this chapter so far. Here's a situation where you can guarantee existence and uniqueness. By existence, I mean you can always solve the initial value problem star, and uniqueness meaning there is only one solution to the initial value problem star. Okay, so if the right-hand side of the equation, capital F, and its derivative with respect to x, if both these things are continuous, say, unlike that previous, in the previous slide, f was y over x, which is no good at 0 when x is 0. So that is not, I mean, by no good, I mean not continuous. Not continuous at 0. So that would lead to some problems. But if x and y are, sorry, if f and partial derivative of f with respect to x are both continuous in some rectangle. Let me draw a little picture. So we have the xy plane here. And suppose you got some, suppose we're thinking about some box in terms of values of x and y. So I color it in here. That's what I mean by R, some rectangle in the plane. So if for all these values in here, I know that f is continuous and its partial derivative with respect to x is continuous. And suppose that x naught, y naught, the things that are defining the initial conditions, lies in the rectangle, where we know we have the good continuity. So if the initial condition, x naught, y naught, is in the rectangle and the function's all good in the rectangle, then there will be a solution to the initial value problem. So you get existence, and it will be unique, so long as you stay within the rectangle. So long as the point x comma y of x stays within the rectangle y. Then this equation will specify a unique solution. Kind of amazing that you can say something so general just by looking at the right-hand side of the equation. That a solution will exist. It won't tell you how to solve for it, but it'll tell you it exists, and it will be unique. Okay, so let's kind of explore some implications of this fact. So, let's consider this absolutely terrible differential equation. The right-hand side is almost unintelligible. It's y times cosine of sine of hyperbolic tangent. Maybe you don't even know what that one is, but it involves it's not so exotic. It involves exponential functions. Anyways, of y times x, you got the x is trapped in here with the hyperbolic tangent, taking sine of that. Anyways, right-hand side is a mess. And then you want this initial condition, y of 0 is equal to 0. So we can ask the question, does the solution to this initial value problem exist? For how long does it exist? And is it unique? And solve it. Okay, well, good luck finding a formula for it. So, good luck finding a general solution to this equation. I doubt you'll be able to. I don't know. Maybe you can. I didn't try to engineer this problem that specifically, but certainly not obvious what to do. You don't want to integrate that thing. Anyway, and you got that x trapped in with the sines and the cos. It's no good. Anyway, However, notice here's one solution to the equation. If just y of x is just always 0, that will solve the equation. Note the right-hand side of the equation is equal to 0 if y is 0, because y is the first. It's y times all this monster stuff. So y equals 0 will solve this equation. Now, on the question of, so we just show that a solution exists, but also notice that the right-hand side is, it's continuous, and partial derivative with respect to x of the right-hand side is also continuous everywhere. So all values of x and y. It's just a composition of sines and cosines. They all are defined everywhere. They have derivatives everywhere. No issues with any of these functions. No issues with any of their compositions. So just by those abstract properties, the right-hand side is continuous, has no issues whatsoever. All right. So by the theorem, we know that a solution exists for all time, for all values of x's. It is a global solution, you could say, and it is unique. Well, I just wrote down a formula for a solution. So I found a solution. So by the theorem, it must be the only one. So it's the only solution to this initial value problem. So kind of amazing, because if we had tried to apply the methods that we had learned so far without investigating this theory, these big picture questions, we would be absolutely unable to produce the solution, because none of the techniques would effectively be able to solve this equation generally. We just kind of lucked into a solution, because I designed this problem specifically to have a factor of y in the front. Same thing would work with any crazy expression of x's and y's following that y, so long as it's continuous. But here we found the unique solution to this problem. If you didn't know about that uniqueness statement and the existence statement, it would have been much harder. So that's kind of the power of these general existence and uniqueness statements. It's not obvious that this, would have worked out in the first place. All right, and that's where I want to end. Thank you very much for your attention, and I'll see you in class.